Hi, everybody. We are getting ready to start in a new section of notes, and this is all about chemical equilibrium, how different chemical equations can happen forwards and backwards all at the same time, and how we can measure those reaction rates. Because remember, we've been studying reaction rates, how fast the reactants change into products, and we want to know how fast the reactants change into products and then change back, because a lot of things are reversible reactions. So these are the notes. I'm going to share them with you because it is kind of long. Last week they were kind of short, so I just had them in the video and you would watch the video. So this week I'm hoping you watch the video and take a look at the notes online. I'll have them saved as a PDF, and you can either copy them down via writing them into your notebook, or if you have a fancy printer, my printer is still not working. If you have a printer, then you can print these off and just kind of glue them or tape them into your notebook. So we are going to take a look at this. Let me see if I can full screen it there for us. Okay. So we're going to start out with, there we go, dynamic balance. That's what this section is called. Dynamic. What does dynamic mean? It means that it's constantly changing. It is not static. Static would be staying the same, but dynamic is constantly changing. So how can we have constant change and balance at the same time? It's chemistry, my friends. Okay, so our big question is, what is equilibrium? And to find out, we're going to be looking at this equation throughout this section of notes. We've got N2, nitrogen, plus 3 hydrogens yields 2 ammonias. NH3 is ammonia. And this equation, this chemical reaction is done a lot in industry because a lot of different industries need ammonia to work. And one of those industries is agriculture. They need ammonia to help fertilize plants. So we are going to look at this reaction throughout. When we look at this reaction going forward, as this arrow indicates, the reactant concentrations, of course, they're going to get used up and they're going to make the product. So they're going to decrease at first, and then the product, of course, will increase. We have 0 product at the beginning, but by the end we should have some. Before all the reactants are used up, though, all concentrations become constant. It's what we see down here in this diagram. It's not that all of the reactants get all used up and they go to 0 while the products zoom up. They all end up right here. See, this is the concentration. We still have quite a bit of H2. We still have a little bit of N2, but they're not all used up. And we have NH3 being made. So here we have the starting concentrations of our reactants. And we know that this purple line is our product because there's 0 when we start. But over time, those reactants will react together and create this NH3, the ammonia, and all 3 of them will be in the state of dynamic balance. So it's considered a reversible reaction. A reversible reaction, a chemical reaction that can occur in both forward and reverse directions. So not to belabor the point, but forward we have the arrow going to the right, reverse we have the arrow going to the left, and you just combine them with the arrow that goes back and forth. It just means that they are reversible. It can go forward and back all at the same time. So that's a reversible reaction. So when we look at this N2 plus 3H2 yields 2 NH3, how does that reversibility affect the production of ammonia? Well, at the beginning, like I said, there's no NH3 present. So therefore, that forward reaction wants to occur. It just happens spontaneously. But as those reactants combine to form ammonia, their concentrations are going to start to decrease. And then as soon as ammonia is present, now it can break down and it's going to do the reverse. So it's all going to happen at the same time. At the point This is important. At the point that the forward and reverse reactions have the same reaction rate, meaning the ammonia is produced at the same rate it's being decomposed, then you have reached this state of dynamic balance or chemical equilibrium between forward and reverse. It's like the game of tug of war, where if the rope is not moving, that doesn't mean that the teams have stopped pulling. They're just pulling at the same level of force. The same amount of force is being pulled on the rope at the same time. So this is kind of the same thing. It is the same reaction rate happening at the same time. We find ourselves in chemical equilibrium. So, of course, let's add some math to this because it is chemistry. So we will look at it this way. The equation for this rate, this equilibrium rate, is going to be using kind of this base reaction. So we have the small letters and then the big letters. I think this should be an A. Let's change that to an A because that's going to bother me. Okay. So we have these small letters and big letters. The big letters are representing the compounds. So down here in this little square, it's really nice. They say A, B, C, D. All the big ones are the molar concentrations. And then the little letters, the littles A, B, C, D in italics, are the coefficients. So if there was any balancing to be done with coefficients, that's where those come in. And then the way you set up the constant expression, equilibrium constant expression, is we put the products on the top, reactants on the bottom, and we put those concentrations of the compounds in there. I'm gonna sneeze. Excuse me. Okay, sorry. We put the concentrations in there, and then the little letters, remember, were the coefficients. So we're going to use those as exponents. So what does that all mean? Okay, let's practice down here. I don't have COVID. Okay, what's the equilibrium expression? Constant expression. We're still using N2 plus H2 yields 2NH3. We put our products on the top, and we put our reactants on the bottom. And you can see here, these little numbers, the subscripts, those are staying with the compound. They are part of the compound. Please, please, please remember this. Okay? So NH3 has to stay NH3. We can't just drop that 3 off somewhere. The bigger numbers, the coefficients, those are the ones that are going to become the exponents. Now here, I don't have an exponent on the N2 because it does not have a coefficient. It's a 1, invisible 1. Okay, so that's how we set that up. Now up here we had 2 products. Here we only have 1, so we just put 1 on the top. No big deal. So what if I had some concentrations for each compound? So you can set up the expression, but now we can actually plug in some numbers and find out what this K, this equilibrium constant, is going to be. So if I give you some of these numbers down here, NH3 being 0.933, N2 is 0.533, and H2 is 1.6. I plug all those in, and it looks like this. 0.933 squared, remember their 2 is up there. 0.533 is N2, and 1.6 to the third, because H2 is to the third. And then I do all the math, and I get 0.399. Please let me know if your calculator does not give you that. Okay, so that is still just plug and chug. The only thing that you need to actually do that takes a little bit of brain power is this part, creating this thing right here, this equilibrium constant expression. Once that's done, like that's the hard part, then you can just plug in all of your numbers and it's easy. But getting this is the hard part. So again, products on the top, reactants on the bottom, use the coefficients. Coefficients, big numbers, those become the exponents. Okay? Okay, moving on just a little bit. This is the end of it. Depending on what that K ends up being, so right up here, K was 0.399. It's positive, meaning it is, or not positive, but it's 0.399. It's less than 1. So if your equilibrium constant is less than 1, smaller than 1, then the reactants are going to be favored at equilibrium. So while they're at an equal rate, we're going to have reactants wanting to be made a lot more. So the value of K is constant only at a specified temperature. Just a little trivia there for you. And equilibrium characteristics, things that have to be true for equilibrium to happen. The reaction must take place in a closed system. We can't have extra things coming in or out. The temperature has to be constant, and all reactants and products are present, and they are in constant dynamic motion. Okay, I think that's it for the notes for dynamic equilibrium, dynamic balance. If you have any questions, specific questions about how to use this equation and get this equilibrium constant, just email me. I'll be available, or you can find another video. Maybe another person explaining this would be beneficial to you. So I'll post another video that you could use if you need that. Again, add these to your notes, especially if you guys are going to go on to any courses like this in college. I already had one of my students do a chemistry class in college and used this notebook. Mind you, it's probably good for maybe the first 2 months out of the whole year, but at least it's helpful in a little bit of a way. So adding more to your notebook is only going to benefit you in the long run. Okay, I hope you guys had a good weekend, and I hope this helped. Email with questions.